It looks small in the sky, almost unremarkable at first glance. A compact point of light surrounded by a faint haze, suspended against the endless blackness of space. To the casual observer, it might seem like just another dim speck drifting silently between the stars. But the longer astronomers watch the interstellar object known as 3I/Atlas, the clearer it becomes that this visitor from another star system is doing something it is not supposed to do. Every new observation deepens the mystery, challenging long-standing assumptions about how objects behave once they enter the sun's domain and raising questions that stretch beyond conventional comet science. The latest image, captured on December 13, 2025, by astronomer Tirasak Thaluang using a modest 0.26-meter telescope in Rayong, Thailand, has become a particularly important piece of this growing puzzle. Although the telescope itself is relatively small by professional standards, the image it produced is anything but insignificant. It is not a single photograph frozen in time, but a carefully stacked composite made from 271 individual exposures, together representing more than 2 hours of total observation time. This technique allows faint structures to emerge from the background noise of space, revealing details that would otherwise remain invisible. The image is presented in false color not to beautify the object, but to map brightness intensity across it. In this format, brighter regions glow more vividly, allowing astronomers to see how light is distributed around 3I/Atlas rather than how it would appear to the human eye. At the heart of the image lies one of the most perplexing features of this object, a compact, sharply defined nucleus. Even after hours of exposure, the light from 3I/Atlas remains tightly confined to a small central region. It does not blur outward into a broad, fuzzy cloud as most comets do when they approach the sun normally. Increased solar heating causes volatile ices to sublimate, releasing gas and dust that expand outward to form a large, diffuse coma. Over time, radiation pressure and the solar wind push this material away, creating the iconic comet tail that always points roughly away from the sun. But 3I/Atlas refuses to follow this familiar script. To understand why this matters, it helps to think in everyday terms. A typical comet behaves like a block of ice tossed onto hot pavement. As it heats up, vapor erupts from its surface, carrying dust and debris with it. The result is a messy, expanding cloud that grows larger and more diffuse the closer the comet gets to the sun. By contrast, 3I/Atlas shows none of this exuberant activity. Its brightness drops off sharply from the center, indicating that little dust is being released into surrounding space. The object appears more like a tightly focused beam of light than a glowing cloud. If most comets resemble lanterns casting light in all directions, 3I/Atlas looks more like a laser pointer, sharp, concentrated, and stubbornly compact even across astronomical distances. This unusual compactness has persisted across months of observations from multiple telescopes and observing conditions. It is not a fleeting anomaly or a processing artifact. The consistency of the point-like nucleus suggests that either the object is not releasing material in the way comets normally do, or that whatever material it is releasing behaves in an entirely different manner. Some scientists have suggested that the surface may be unusually strong or depleted of volatile ices, perhaps hardened by millions or even billions of years of exposure to interstellar radiation before entering our solar system. Others have proposed that outgassing could be occurring in a highly collimated way, releasing material in narrow jets rather than in a broad, isotropic flow. Yet even these explanations struggle to account for all observed features. The compact nucleus, however, is only part of the story. Extending from 3I/Atlas is another feature that has proven equally difficult to explain, a persistent sunward structure often described as an anti-tail. The term itself is misleading and, in many ways, inadequate. In ordinary comets, anti-tails are rare and temporary optical illusions. They occur when Earth happens to pass through the plane of a comet's orbit, allowing previously released dust to briefly appear, as though it is pointing toward the sun. As viewing geometry changes, the illusion disappears, and the anti-tail vanishes or shifts direction. That is not what is happening with 3I/Atlas. The sunward feature associated with this object has been observed repeatedly and consistently, refusing to behave like a mere trick of perspective. It was present in the very first Hubble Space Telescope image taken on July 21, 2025, when 3I/Atlas was still approaching the Sun from a distance of nearly 3 astronomical units. It appeared again in a second Hubble image on November 30, 2025, after the object had passed perihelion and was moving away from the Sun. In between these dates, thousands of ground-based images captured by astronomers around the world confirmed the same unsettling pattern. The feature does not vanish, does not rotate away, and does not behave as geometry alone would predict. What makes this particularly striking is that the sunward structure persists despite changes in the object's distance from the Sun, its viewing angle from Earth, and its orbital position. In normal cometary physics, such stability is difficult to achieve. Dust and gas released from a comet are strongly influenced by solar radiation pressure and the solar wind, which rapidly push material away from the Sun. A feature that consistently points sunward suggests either an entirely different physical mechanism at work or a property of the object that defies standard models. One possibility is that the feature is composed of unusually large or dense particles that are less affected by radiation pressure. Another is that it represents a continuous, directed emission of material from a specific region on the object's surface, perhaps driven by localized heating or an internal process not commonly seen in solar system comets. More speculative ideas suggest electromagnetic effects or interactions with the solar wind that are not yet fully understood. Each hypothesis, however, introduces new questions and complications, underscoring how little is truly known about objects formed around other stars. The interstellar origin of 3I/Atlas adds another layer of intrigue. Unlike typical comets, which formed alongside the planets billions of years ago, 3I/Atlas was born in an entirely different stellar environment. Its composition, structure, and thermal history may reflect conditions far removed from those that shaped our own solar system. The object has spent most of its existence drifting through interstellar space, exposed to cosmic rays, supernova shock waves, and the harsh radiation of the galaxy. By the time it wandered into our Sun's gravitational grasp, it may have already been fundamentally altered in ways that make it behave unlike anything astronomers have studied before. In this sense, 3I/Atlas is not just a curiosity, but a messenger from another star system. Its strange behavior offers a rare opportunity to test and refine theories of cometary physics, planetary formation, and interstellar processes. Every observation acts like a clue in a larger investigation, hinting that the diversity of small bodies in the galaxy may be far greater than previously imagined. What appears at first glance to be a faint, unremarkable point of light is, upon closer inspection, a challenge to our understanding of how matter behaves when it crosses the boundary between stars. As telescopes continue to track 3I/Atlas on its outbound journey, astronomers remain keenly aware that this object will not linger forever. Eventually, it will fade from view, slipping back into the darkness of interstellar space, perhaps never to be seen again. Before it goes, scientists are racing to gather as much data as possible, knowing that each photon captured may hold insights that will take years to fully unravel. Whether 3I/Atlas turns out to be an extreme example of natural cometary behavior or something entirely new, its silent passage through our solar system has already left a lasting mark on astronomy, reminding us that the universe still holds many surprises, even in the smallest and faintest points of light.